Why hello lovely humans, Jen Foxbot here in another exciting edition of Math Mondays! Do okay, a little impromptu theme song there. So in this episode I'm going to talk about accuracy and uncertainties. Those two go hand in hand and they are both super important whenever we're talking about any sort of number. Particularly when we're talking about numbers that deal with the real world, that deal with our lives and things in it. Things that we're trying to make sense of, or maybe not make sense of. Doesn't really matter. But what does matter is being upfront about how accurate your numbers are, as well as any errors or uncertainties in your measurements, and being transparent about what those uncertainties are. So this is super helpful if you want to learn how to read scientific papers, if you want to learn how to understand studies. So for example, like all of these polls that are super popular during midterms and things like that, understanding accuracy and uncertainties will help you really translate what these polls and other data sets are telling you. Because it's kind of like this, like reading between the lines sort of thing. Once you understand accuracy and uncertainties, you can look at these numbers and really translate them in your head to recognize like, oh, okay, these numbers are applicable in this scenario, but not so much here. And, you know, I can rely on them in these circumstances, but not in these. So super helpful whenever we're working with numbers. Yay. All right. So, what is accuracy? Well, accuracy is a little hard to define without the word itself, but basically it's like how precise, there we go, how precise our measurements are. Accuracy tends to depend on the numbers that we're starting with. So if we are given certain values, say for example the radius of the Earth, many other people have calculated that, and so that number will come with a certain number of significant figures. So say for example, hold on, I do not have this one memorized. The radius of the Earth is 6.36 times 10 to the 6th meters. Okay, so this number has 1, 2, 3 significant figures. That's fine. Sometimes we can ignore the first number because it's like you need a number to start with. So sometimes you might say that these are the significant figures because that's how accurate your first number is. So we'll just say this has 3 significant figures. There are 3 numbers that tell us the radius of the Earth. If I were to write this as 6.3 times 10 to the 6th meters, because we like SI units here, or we like the metric system, then this number only has 2 significant figures. So this number is less accurate than this first number. You could probably see where I'm going here. I can also write 6 times 10 to the 6 meters. This only has 1 significant figure, and this is the least accurate number. And conversely, I can go, and if I wanted to be really precise, like let's say I was doing rocket science, you gotta be really accurate, because if you're off by a couple of digits, it means that your Mars rover will not end up on Mars. It'll end up in the depths of space. Oh no. Curiosity, no, it'll get lost. Oh. So accuracy is really important for certain types of calculations. For other types of calculations, we don't really care. For most of the stuff that I'm doing estimates, and a hand wavy, this is close enough, is good enough for me. So I might pick something like this with only 1 significant figure because I might be more interested in doing mental math. Not a problem. As long as I'm transparent and upfront about what my numbers are, what the accuracy is, and what my conclusions are, which includes how accurate my conclusions are and the limitations of my measurement. So if I were to use a number with only 1 significant figure, I can only give you back a number with one significant figure. So let's say I wanted to calculate the diameter of the Earth, which is just 2 times the radius. I want to be lazy, so I'm going to say, oh, well, that's easy. It's just 12 times, here, we'll label this like good scientists, 12 times 10 to the 6th meters. That's good enough for me. That's cool. If I wanted to be super cautious, I might actually say, since I'm starting with one significant figure, it might be more appropriate to say it is about, whoopsies, that got a little out of hand. It is about 10 times 10 to the 6th meters. So this number only has one significant figure. This number actually has 2 significant figures. So one could argue, if you're trying to do really good science, this would be more appropriate because you're sticking with the same number of significant figures that you started with. Cool. And conversely, if you needed to be more accurate, you would just go find someone who is more precise, and you would get a number that had more decimal places or more significant figures. There you go. All right, so that's significant figures and accuracy. Where does that come from? Well, let's take an example. Let's say I wanted to measure how high I could jump. Ooh, fun. So I wrangle a friend to hold up a stick for me, or maybe we tape a measuring tape on the wall. In that case, what is the accuracy of my measurements? Can I go around and tell everyone that I can jump 8.36 feet high? Well, maybe. It depends on how precise my measurements are. If I'm using a ruler like this, a lot of times accuracy is determined by the markings on your measuring device, or how accurate your measuring device could be. So you will notice, it might be a little blurry, but there are more lines in the lower numbers of my ruler and not as many lines as you go out. So the longer the thing is that you're measuring, the fewer lines you have to compare. And that means that you can be more accurate because there are more lines. It's an easier way to tell what fraction of an inch you have. What's convenient is that on the metric side, all of the lines are equal all the way across. If I zoom out like that, huzzah! So actually, this is kind of interesting. So you can be, it doesn't matter if you're using the metric side, your measurements are going to be accurate all the way from 0 centimeters to 30 centimeters. But if you're using inches, your measurements are going to be more accurate between 0 and 6 inches than they are between 6 and 12. So let me back up really quick. Accuracy, the accuracy of our measurements, a lot of times depends on how we are measuring them. So in this case, if the thing I'm measuring is 10 inches long or somewhere in that ballpark, the most accurate that I can say my measurement is 1/8 of an inch. Well, really, 1/2 of an eighth of an inch, right? Because if we have something that's 10 and 1/8 of an inch, it's going to be somewhere in between those two lines. So if we say that our accuracy is 1/2 of that, that's reasonable. And if we're transparent about where the accuracy comes from, that's what's really important. So again, accuracy depends on the limits of the thing that you're using to measure. If you have a more accurate ruler, like let's say you have a digital ruler, cool, that would be more accurate because that's going to have a digital readout with a certain number of significant figures. So that's the first thing, accuracy. Depends on how we're making our measurements. And then the second thing would be uncertainties. So uncertainties are basically a way for us to account for sources of error. And there are 2 types of sources of error. You have random errors, which are like us humans being a little clumsy sometimes, and maybe, like dropping the measuring stick, not quite getting a reading. Or maybe we move it a tiny bit. If I had my friend holding it, they might take a step back and then all of a sudden that's a random error. I don't know how to account for that. Oh no! So random errors typically result from some sort of human cause. or environmental cause. My dog likes to join into my experiments sometimes, so maybe my dog bumps my measuring stick, and now I have a source of random error. So that's the first type of uncertainty. The second type are statistical errors, or basically like if you are taking a measurement and your ruler is consistently offset by a few inches, then you would have a statistical error. I feel like I'm calling it the wrong thing, but anyway, you get the gist. So basically those types of errors are errors that are consistent. We could identify that source of error and subtract it out of our data and get more accurate data. But random errors we're kind of stuck with. That's the world we live in, and we have to be upfront about where they come from. All right, so I want to give a quick example to really drive this home. So let's say that we wanted to actually test how high we could jump. Woo! Like that. Yeah. Okay, so you wouldn't just do one trial, right? You would do at least 3, probably more if you wanted to be super accurate. The more trials you do, the more accurate your data is. But you also have to be really careful because let's say you do 100 jump trials. Whoa, that's crazy. You're probably going to get a little tired, maybe by like 99 or maybe by like trial 9. And so on trial 100, you're not going to be able to jump as high as you did that first time. I find this a lot when I rock climb. Sometimes the first time I try a problem, it's a lot easier than the 15th time that I try it. And it's because you get tired. So, oh my gosh, you can't just do a bunch of trials when you're using your body because your body gets tired. That's a source of error. And so that means that you have to be very careful about how you're designing your trial. You have to take into account all of the specifics, like how many trials are you going to do? How are you going to keep those trials the same? You have to wear the same shoes in every single trial. Maybe you need to do all of those trials at the same time of day. So for example, let's say you come home from work and you do the trial. You wouldn't want to do it in the morning the next day because, well, you don't know what your body was feeling like after work. And the way that your body feels in the morning is going to be totally different than the way that it feels after work. So to keep your jump trials consistent, you need to do them at the same time of day. Maybe you would need some sort of control group or something to compare it to. I'm not quite sure what a control group would be for a jump trial of just yourself. But something that maybe it would just be like the way that you are living your day. I don't know. Anyway, moving on from that one. But you usually do need a control group. That comes up in medical trials a lot when you're figuring out if medicine is effective. Basically, you give a certain number of people the actual medication, and then you give a certain number of people a placebo effect, and then you tell them it's the medication. And if the medication is more effective than the placebo group, then you can say that the medication is effective at treating X condition or treating this certain condition that you were studying for. So yeah, there you go. The placebo effect is actually real, but medication is verified against the placebo effect. So when your doctor is like, hey, maybe you should take some ibuprofen, it's because ibuprofen does actually work better than the placebo effect. And now you know. Woo! Okay, so yeah, when it comes to designing studies, we have to be very careful about how we design them. This also is super handy for when you're trying to understand how reliable or how accurate a particular science paper is. So you need to look for the way that they collected their data. You need to look for the assumptions that they're making, because in my jump trial, you know, I'm assuming that I'm going to jump in the same way every single time. It's not really true. I can't possibly jump exactly the same way in every single trial. One time my left foot might be all the way over here, or one time my right foot might be slightly back. It's going to be a little different every time. And that's okay as long as we are transparent about our data. Cool. So I'm going to leave it there because this video got a little long. I'm very passionate about this, as you could probably tell. And as usual, this is open to y'all, so please share your math questions or the types of problems that you want to work on, the types of concepts that you're interested in. If you're 10 years old and you want to learn calculus, let's see what we can do. But let me know, because I want to make sure that we are covering the things that you are interested in, because math is awesome, and I want to share my love of math with y'all. Cool. All right. Let me know if you have any questions about accuracy or uncertainties. If you have a particular scientific paper that you're trying to understand, or if you're not sure if it's believable, let's share it and talk about it, and let's see if we can understand data a little bit better. All right. Thank you for watching, and see you next time. Bye.